Right. How to find the length of a curve on surfaces? Okay, how do we use the data from on the surface to study the curves? So if we have a curve in a three-dimensional n-dimensional space, okay, so here's a curve, C, right? This is in Rn. Really doesn't matter which dimension, okay? So if you can parameterize it, okay, you know, it's a map. It will be image of some interval from A to B, okay? Then the derivative of a sigma t is going to be the tangent vector to the curve, okay? And we find out this is going to be an invariant. It's really independent of the it's really independent of the choice of particular parameterization, okay? So this is called the differential of the arc length. So if you hear right here, this is S is arc length. So differential of the arc length is going to be the length of the tangent vector times dt. Okay, so this is called differential arc length. So the total length is going to be the integral from A to B, and the if you do not specify, here's our notation usually in geometry. So this is a put a C here if I do not specify the parameter. Okay, so this is the length of the curve. And if you want to use a parameter t, then that's from A to B. And this is how do we, okay. Now, if you have another parameterization, for the same curve, a tilde, b tilde, and the sigma tilde and t tilde, okay, then you will see that this is going to be the same, okay. So this will be a tilde, b tilde, and if you use another parameterization. So really doesn't matter which one you choose. Okay, so this is about the length. How do we take the length? Now we consider curve C on a surface S. Okay, that surface in S in R3. Okay. So now you have a surface, you have a curve, okay, on the C. Okay. Well, if you view the curve in the space, if you view the curve in the space, then you can then just you can calculate the length, right? Okay. So let's find the map. Okay, this is sigma t, and from A to B, it's the same, right? Okay, just view C as a curve in the three-dimensional space. Then you have this, right? And I'm going to put a square there. But without square, this will be, then you have this, okay? And the length of the tangent vector. So now I'm going to describe the length of the tangent vector. I'm going to describe the length of the tangent vector. Okay, so this is the length of this tangent vector, right? How can I? I'm stupid. I should use a sigma because I've been confused. Okay, I'm going to use a gamma. Okay. So for the curve, a typical notation for the parameterization is gamma, not C. Okay. So all C, and sometimes the curve is using C. Okay, we can use a C. Yeah, C is a curve. Okay, C times C. Okay. Yeah. Now, because this is on the surface, I can find a surface patch for that. That's called sigma. Okay, this is in the UV plane, right? So that this portion of the curve, this portion of the curve, okay, is going to be here. Okay. All right. So you can always C over T can be always written sigma U of T, V of T, right? Okay. So at every point here, so this is the point sigma, not sigma, C over T, and this will be U over T and V over T. Right. Now the curve can be maybe occupy the whole surface, but my surface patch, it's only covers small neighborhood, and that's just local version. Okay, locally can describe that. Right. So let's take a sigma C prime T. So use a partial derivative. Use a chain rule. Okay, use a chain rule. Okay, and I have this. Right, there's a chain rule. And the length C prime T square, which is C prime T dot C prime T. Okay, it's a dot product in three-dimensional space. You can use dot product. Otherwise, you have to use the inner product. Okay, in general, in high dimension, you don't have the dot product if it's a three-dimensional vector. Right. So how can I do that? So for the simplicity, I'm not going to mention T here. Okay, sigma V prime dot sigma U prime dot sigma V prime. Okay, just for simplicity, I'm not going to put all of it. Right, so just multiply them out. That's a sigma U dot sigma U prime squared. And then this will be sigma V dot sigma U prime U prime. Then I have another one, sigma U V and U prime V prime. All right, but those two are the same. Those two are the same. So you can, I can express in the form like a E prime square and 2F U prime V prime and GV prime square. Now, what is U and what is the E? E is a sigma U dot sigma U. F is a sigma U dot sigma V. It's the same as sigma V dot sigma U. Okay, and G is going to sigma V dot. Okay, those are the functions. Functions of U and V. Okay, local function. So what does that mean? Okay. That means C prime T dot C prime T, roughly speaking, is going to be EU prime square 2F U prime V prime. You can calculate using the data in the just this this is the mode here, right? So it's a curve. Remember the curve, right? In two-dimensional space. The corresponding curve, right? So what is U prime V prime? U prime V prime is just the tangent vector in the vector space UV, right? So U prime V prime. Okay. Okay. So there is extra part here, EFG. Okay. This is a tangent. This is on the surface, on the surface, C prime T. So the dot product. This gives us the square of the length. This gives us the square of the length. Okay. This gives us the square of the length. This gives us a square of the length, of this tangent vector in three-dimensional space. Here's a three-dimensional space, right? Two-dimensional space, right? So you see the correspondence, okay? We wanted to calculate the length, square of the length of this tangent vector. you just need to find the corresponding curve in the UV plane, and then the tangent vector. But this is not even the length of the tangent vector. Actually, it's complicated. You know, this can be written in the form like that: U comma V prime, E F F G U comma V prime. Okay, can be written. There is something, another matrix there. Okay, it's not going to be. This is not going to be U comma square plus V comma square in general. Okay, it's nothing. So there is additional matrix you can use. Okay, so this is how do you get, and then okay, in case if C is completely contained in this domain, okay, which is on the surface, you know, on the surface, then the length, you can just use this single one, right? So the length, the length of C, first of all, it's integral, right? Why square root that? Because the length of this is the square root of the dot product, okay? But you can translate it to, this is an abstracted notation, right? So you can translate into integral of the function using the surface patch. Right? So that can be using, you know, just E U comma square, 2F U comma V comma, and G V comma square and dt. Okay. Yeah. So naturally, you will get something here. You will get something here. You get a quadratic form, right? So we get a quadratic form, right? How can I define the quadratic form? Very point. This is a quadratic form. I use this one. I use this notation. Okay, and how can I? Yeah. So I get a quadratic form. Okay. So this is going to be V and the V. Okay. And that is going to be. It can be, you know, another unit plot. Okay, but I can use that. I can define in the following way. Yeah, let me put. I'm going to use a different notation. That's vector. Yeah, use a capital. Let me use a capital V. Otherwise, it's confused within my notation. Okay, so this is going to be E UV lambda square plus 2F UV lambda mu plus G UV mu square. Okay, and where capital V is lambda sigma U UV plus mu sigma V UV. Okay. Also, this is a tangent vector on the sphere, and this is well defined. Okay. This is well defined. It's a quadratic form. It's well defined quadratic form. When you change the surface patch, you're not going to change it. Okay. So this is called second fundamental form. The first, second fundamental form. First, so I is called the first, second fundamental form. Okay. So I is actually point P at the point P. So this is this is a function on the tangent vectors that's quadratic in the above sense. We have lambda square, lambda mu, okay? So this is called the first fundamental on the surface, right? Of the surface at the point, okay? It's expressed in terms of a surface patch. Second fundamental is really independent. It's really independent of choice of a surface patch. Okay, but they can express using a surface patch. Okay, because otherwise, how do you compute it? It's pretty abstract. So roughly speaking, this is nothing but just a v dot v. Okay, in the abstract case. Okay, in the abstract case. Okay, so v is a tangent vector, but it's viewed as a vector in R3. Okay, it's viewed as a tangent vector. It's a space like that. Okay, so here's a v. It's tangent vector. But the v is also can be viewed as a vector in three-dimensional space. We can talk about that. Okay, let's derive this above formula again. Okay, at the very beginning we use a matrix, right? Use a curve, but without using curve, you can also do like that. You express left lambda, right? Because every tangent vector can be expressed in this form, right? Every tangent vector can be expressed in this form. Then, and this is my definition. My definition without using, the definition itself does not depend on the choice of surface patch. You can use surface patch to calculate, right? So that is going to be v dot v, so it's going to be lambda sigma u, and plus mu sigma v dot lambda sigma u plus mu dot v. So when you multiply this out, you get okay. So it's nothing but e lambda square 2 f lambda mu and j mu square. Okay. All right, so that's the so-called second order form. The first fundamental form. So first one is defined as v the tangent vector, the dot product with itself. By using, because this is tangent vector, so you can express it in terms of the surface patch signal, right? And you can use that to do to compute the length of the curve. Okay, just square root, right, of that curve. So let's take a look at some examples. Right? Let's take a look at some examples. Oh, by the way, there were some other notations. I can talk about this a little later. Okay. So here, consider surface, a surface of revolution. Right. So the surface of revolution in the space. Right. Okay. Okay. Remember the premature, surface patch, right? Surface patch is from UV, right? And this is going to be All right. So using that, all you have to do is just to find the partial derivative. Right. Then sigma v. Right. All right. So then you calculate the E and FG. So the dot product, I find out the cosine V, sine V, sine V, cosine V, and then have a negative sign strong, so it's 0. Okay, it's a 0. Wait a minute. Sorry, not this. F is 0. E is not 0. Okay, E is sigma u itself. Let's be careful about this. The sigma u dot sigma u. Okay, so just the length of that vector, so the F comma u squared and G comma u squared. Okay. And the F is 0. Okay, so sigma u dot sigma v is 0 here. Then sigma v is going to be F squared. Right. Now, now if we assume, okay, if we generate the surface of revolution using curve, okay, so you let gamma u to be to the curve. Okay, that is the curve is the f of u, and the g of u. That's the way how do we use that to the first component, that's why how to calculate. This is a curve. Okay, so you notate. So this is a curve, gamma. Right? So this curve, if we assume that this is the curve we use it to generate the surface revolution, right? Right. Now, we may assume that gamma prime u is going to be 1. The length is going to be 1. So that means f prime u squared plus g prime u squared equals 1, right? So in that case, I think my e's are going to be 1. F is 0, right? And the g is just f of u squared. All right, so my second fundamental form, right? So for the vector v, lambda sigma u, mu sigma v, the second fundamental form, the value second fundamental form is just equal to lambda square, fu square, and the mu square. And you can calculate the length of the curve using this formula. Okay? Yeah. So we can, this is a surface, right? So you may want to find the length of the curve, right? On this surface, right? So if you want to calculate the length of this curve, you just need to know the coordinates of this point. Right? Coordinates of the point on this curve. So if you have a gamma, if I have C over T, it's going to be sigma U over T, V over T, right? Okay. And the T is between A and the V, and the length C is going to be the integral, right, from A to B. And actually it's going to see C power T, dot C power T, right, square root. But that is actually the first fundamental form, right? And the square root. And if using above formula, you can get in the place of lambda, I get a U power square. In the place of U, it's a V power. This is U, this is a V, okay? Yeah, so that's the formula. So if you have these two functions to describe this curve on the surface of revolution, then you can just use the first fundamental. If you already know the first fundamental form, use the coefficient of first fundamental form, you can quickly get the integral for the length of the curve. Okay. Yeah, there are some notations in the book. The notation is du is a linear map from R, okay? And of course, sigma is u to the surface, okay? The surface patch. Then it has components, right? Sigma, u and v, right? And uv as a component. So I needed to introduce what is du. Right. So this is surface, here's a point, this is tangent plane, right? TPS, and here's a sigma map, right? This is my domain, right? And the point P is spatial, right? Right. So then I have UV, and du is going to be, maybe more precise at DUP, and sometimes we will remove the point here. DUP by definition is going to be, it sends the tangent vector to 1. It sends other tangent vector to 0. Okay? And then DVP is the opposite way. That is going to be 0. That's going to be right. So in other words, for any V, for any capital V lambda, sigma u, mu, sigma v, any tangent vector, and du to v is nothing but just lambda. Okay? dvp, capital V is going to mu. Okay? So that is, you understand that, right? So similarly, if dup square acting on V is just the dup V square, okay? The same. And the dvp square capital V is dvp square, okay? That was just 2 there. You know, just like f squared, you know, x is given fx squared. Because this is a common notation. Okay, using that, we may assume, right? Then if E, now remember E lambda squared plus 2f, right? Okay, I'm going to, if you want to put the points here, it's fine. So E and the lambda squared, right? Plus 2f lambda me and plus G mu squared, right? Okay. Since lambda is just how to get a lambda, right? Lambda is the IUPUI square. So right. Right. And the last one is G DVP capital V square. Okay. So sometimes for simplicity, you don't need to put the V there. So therefore, the first fundamental form just simply written as E and DUP square 2F. Yeah, I still want to use a specific point. Okay. Okay. So that is going to be square of 2FT and DUP DVP, right? And then G. Oh, I don't need I use a P here. That's yeah, it's P. That is a special point. Okay. Okay. Or further, you just without the mention u down to do not, right? You just simply write E du square and the 2F du dv and the G dv square. Okay, that is called first fundamental form. Okay. Okay. It is at a particular point. It is quadratic form on the tangent plane. Okay. It is a quadratic form on the tangent plane at every point. Okay, in this domain on the surface. Okay, so because I have to use a sigma to define EFG. All right, so let's go back to the specific example again. Yeah, let's consider another example. Consider another example. Sigma UV, I just described the surface using surface patch. Okay, it's a gamma U plus V delta U. Okay, what does that mean? So you have a bunch of curve, you have a curve, then you have along the curve you have these lines. Okay, those lines are determined by the direction delta U. Okay, so this is a curve, gamma U. Okay. Right, so let's compute it. Let's do it. All I have to do is compute E. Okay, so let's compute it, figure minus sigma. Okay, so it's gamma term. Okay, and sigma V is going to be yeah. Okay, so E is going to be gamma prime plus V delta prime, and Okay. So it will be gamma prime, okay? And twice of V delta prime gamma prime, and the plus of V square delta. Okay. F is going to be gamma prime delta plus V delta prime delta. Okay. And the G is going to be delta. Okay. Now we may assume, okay, look at that, look at the curve, right? We may assume this is the delta. We may assume it's a unit vector along the curve, right? Okay. Not only that, then immediately you have this going to be 0, right? It's going to be pretty simple. Okay, I also have to assume that this delta, if it's delta is normal vector, this is gamma, right? Gamma prime. So you can, this is a, yeah, it's gamma, right? So you may assume that this is a perpendicular delta, right? Let's first assume that delta is a normal vector to the curve, okay? So we also assume this is going to be gamma prime is going to be 0, okay? So that means it's a family of vectors, vectors delta along the curve. It's perpendicular to the curve. Right. So now it's relatively simple. G is going to be 1. F is going to be what? It's going to be 0. How about the E? Okay. Right. How about the E? I think the E, I can assume gamma prime. This is also going to be 1. Okay. So the curve it has unit length. It's 1 plus. Let's take a look at what is G. 2V. Okay. 2V delta prime delta. And then V square delta prime delta. You cannot go further, So this is a formula. But if you really want, you can have a couple choice for delta, okay? There are 2 choices for delta, okay? One is that the delta could be the normal vector of the curve. Okay, if the delta is the normal curve, then what? This is a t, right? And the delta is normal vector, right? Okay. So what is delta prime? Normal vector prime is going to be, it's given, right? I think it's k something. Yeah, it's given here in the page. Yeah. So it's going to be negative curvature k and the t plus tau and the b. Right, so let's take what is the e, right? So e is going to be 1 plus twice of v delta prime times t. So the product of this is actually negative k. Right? T times t is 1. Yeah, this just product is the unit product is 2. Okay? Then delta R it's going to be negative k squared plus r squared. So you get a you get a polynomial. So this part together it's going to be 1 minus kv squared plus v tau squared. Okay? In general, it's not going to be 0. All right. So you get pretty nice formula for this case, right? Yeah. The second case is when the delta is b. Right? If delta is b, gamma prime is t, but delta is b, so b delta prime is going to be negative. Delta prime is going to be negative t n. And negative tau. Okay. Okay. So let's go back to our computation. Right? The only problem here is E, right? So E is going to be 1 plus 2g gamma prime delta prime v squared delta prime delta. So let's calculate 1 plus 2v delta prime is negative tau n delta gamma, right? This is 2. Okay. Plus v squared negative tau n negative tau n. Okay. So what we got here is the dot product n and t 0. So you only get 1 plus tau v squared, or even shorter. Okay. That's it. So you have a two fun. Based on how do you construct a surface? Are you going to use a normal vector, right, to construct the surface? So the first case, look at the picture here. This is a curve in space. This is a plane, right? And you compute it. That's going to be normal vector. So your surface, the surface is always looks like that. Okay. The second case, yeah, this is the n direction, right? The second case is quite different. You know, this is the n, but we are talking about this b. So it goes like that. You know, it's hard to draw it. Okay, it's another 3D. So I try to draw it. Those are the vector b, vector b. Okay, so the normal vector is in that direction. So this is a different type of surface. You can construct a two nice family surface. And another surface is called tangent to the curves T. Okay, you can also get a very special surface. If we let the delta to be, yeah, the third case is if delta is capital T. It's possible. If delta is capital T, I cannot assume it's perpendicular to T. So you have to go back. So I'm not going to do this. Okay. Okay. Yeah, you have to redo it. You have to consider. And I already assumed that my delta is perpendicular to the plane. So those are two examples, right? Okay, our next problem, I just wanted to be more specific one. Okay, so here's the example. Okay, sigma u and v is going to be u, v, it's graph, right? F, u, and v. Okay, let's take a look at that. The way to can do the graph. X, v, f of x. I can handle choice right. Let's do the whole. Sigma u is going to be 1, 0, u. V is going to be 0, and then 1 after. Wow, pretty quick. V is going to sigma u by u. 1 plus f u squared. F. Okay, it's just sigma u by sigma v, so it's just f u. G. So those are the formulas. So for attaining the vector, not vector, for attaining the vector, to the surface, okay? At the point x, y, and so let's see, just at the point of sigma, okay, sigma u. Okay, so that is going to be lambda, sigma u, mu, sigma v. Okay, since you already did a computation, it's going to be lambda 1, 0, after u, right? U 0, 1, after v. So this can be written as lambda mu lambda fu mu fu. Okay, not too bad. So this is a tangent in general. This general form of the to the graph. Okay, now you can calculate without using a bar formula. You can calculate, right? So the first fundamental form is just v part of v is the unit form. Okay, so that means you already know the vector components. So lambda square plus mu square plus lambda fu mu fu square. Okay, this is a project. But you can get this from above, right? So it's going to be lambda square fu square 2 lambda mu fu v mu square fu square. So the coefficient of lambda, you have 1 plus fu square lambda square, and you have twice the lambda u fu v, and then you have v square mu square. So this is my E. That is my F. That is my G. Okay. G is 1 plus F v squared. E is 1 plus F v squared. Right. And you can use that to compute compute the length of a curve on the surface of the graph. So once you have a surface, then you can, once you have the first fundamental form, you don't need to compute it all the time. All you have to do is just use the EFG to write on the formula for the integral, for the curve and the graph. That's for the curve on the graph. V equals f of x, y, right? How do you describe it? Well, CLT is really, right? X of t, y of t. If you use a component, right, so it's just u, v. If you use the extend the surface patch. Okay, it's better to do that. Okay. So you have a U of T, U of T, and F of T. Okay. This is a trick. Okay. So V C power T is C power T dot C power T. This is the dot product. If you use above formula, you can do directly in the computation. It's going to be U power T square, like U power T square, and you can have a U power, V power square. Okay, so you can always use this. You can get it from here directly, or you can just find a dot product, the median. The dot product that gives the square the length of the curve. Okay. So the length is going to be the integral from A to B okay. All right. So finally, let's take a look at some situation. Okay. I'm going to consider sigma u from this is a surface patch. I'm going to look at the consider surface patch. Right, so this is surface, and I have a surface patch. Then I have a second fundamental form, right? My first fundamental form. It's an E du square, 2F du dV, and G du square. E, F, G are functions of dV. Right. Right. I want to prove the following statement. EU of the EV equals U equals 0. You can only if sigma UV is parallel to the normal form. Yeah, so that means this is normal form. Yeah, right? Yeah, EV means what? EV means E is a function of U. GU equals 0 means E is a function of U only, and G is a function of V only, right? This sometimes happens, right? All right, let's prove this. E is sigma U dot sigma U, right? So EV is going to be twice of sigma U V dot this, right? Right? And the G is a sigma V dot sigma V. So GU is going to be sigma UV dot sigma V twice. Okay? So EV equals 0 and GU equals 0 if and only if sigma UV dot U0, sigma UV dot sigma V0. Right? If and only if sigma UV is perpendicular to sigma U, and sigma UV is perpendicular to sigma V, right? Okay. So if and only if sigma UV is parallel to the cross product. But this is just a multiple of the normal vector. It's parallel to the normal vector. Normal vector is defined to be it's normalized, right? So we get exclusion. Yeah, there are some first fundamental forms of the positions are quite special. Then they imply some. They imply something, right? So in this particular case, U is just a function. G is a function of U, and V is a function of U. So that means the fundamental form is E U U square twice of F. I don't care about N plus G GV, right? So GV DV square if and only if sigma U V parallel to the N. Yeah, I think that's all I want to talk about today. And well, maybe I should do one more example. Let's understand, if there are any examples make satisfy this condition. Let's trying to figure it out. Okay. Yeah, let's take a look at the example. When you make assumption in mathematics, you have to give an example. Otherwise, this assumption does not make any sense. Right. So let's go back to the graph. So E is a function of, let's consider the sigma, right? U and V. It's U and V f of U, right? I want to see under what condition, right, is satisfied. Right, so E is going to be 1 plus f of U squared. Right, f is going to be f of U, f of V, right? G is going to be 1 plus f of U squared. For this case, it's harder to get, okay? EU, yeah, EV, right? EV is going to be, right, it's twice of FUV. So GU is going to be twice of V FVU, okay? We cannot assume FU is 0, FV is 0, right? We may, so otherwise become true, constant, right? So this is 0. So if FU square, FV square, we do not assume all of them 0. At least one of them, right? Then EV equals 0 and U is 0 if and only FU is 0. Now, what kind of function the partial derivative this is 0, right? So you find examples, satisfy this condition among the graph. But for those partial derivatives, f u v 0, right? Can you solve it? What kind of f u v, right? F u v 0, then f u is going to be a function of lambda u, right? Okay. So then you the derivative, then f it's a plus. Let's see. F of u depends on u only. Then f is going to be integral of lambda u du, right? Plus another constant c. Now that c could be a function of a v. So when you differentiate, you get, right? So anyway, so the function can be any function like au plus bv, okay? au plus bv. Then when you differentiate with respect to u with respect to v, then it's going to be 0. Okay? So you have a lot of graphs with that property. Okay? Lots of graphs with that property, but not necessary to be a plane. Okay? Yeah, we understand the first fundamental form. Those are just a quadratic form on the tangent space. Tangent space is a two-dimensional plane. Okay? And we use that. We got this from finding the length of the curve in the space, what's on the surface. Okay? Then we got this so-called the first fundamental form. Then later we can use that to find the length of the curve. Okay? Back forward. Essentially, this is about the length of the curve. The square of the tangent vector. Right, so first fundamental form just a quadratic form on the tangent space. So I'm going to stop it here.